What's going on, everyone? Welcome back. Patrick here, and moving on to the next video, another limit question. So we got the limit as x approaches 2 of x minus 2 all over the absolute value of x to the power 3 minus 2x squared. So first we have to graph this function, and then we're going to find the limit. And notice that this function, very similar to the previous video, so I'm going to follow very similar steps. And if you didn't watch the previous video, I recommend you watch that one first before watching this one, just because I'm going through the steps for the first time in the previous video. So I probably go into a little bit more detail. In this video, I might go through it a little bit more quickly. So, like in the previous video, first thing I'm going to do is actually rewrite this function into a nicer form. So notice that here we can factor out an x squared in this expression, and we'd be left with x minus 2. It's gonna have and that's still all within the absolute value. And then, if you remember, whenever you're multiplying two things within an absolute value, you could just take each of those things separately and put them in their own absolute value. So we could take this x squared, put it within its own absolute value, and then this x minus 2 we could put within its own absolute value as well. Also, like the previous example, notice that there are two x values that make the denominator equal to 0. An x value of 0 here would make this entire denominator equal to 0. And then an x value of 2 would make this equal to 0, and then 0 times that, which would be 4. If we plug in 2 there, 0 times 4 would give 0 in the entire denominator. Now, notice that at an x value of 0, if we plug in 0 for all the x's, what we'll end up with is negative 2 in the numerator and then 0 in the denominator. And as I mentioned, whenever you have a number over 0, that means that at that x value, it's going to be a vertical asymptote. And then notice if we plug in 2 for all the x values, we'll end up with 0 in the numerator and 0 in the denominator. So we'll end up with 0 over 0. And whenever you have that, it means that there's going to be a hole, right? Because notice that those factors are going to cancel out at that x value of 2. So this function here that we just derived is basically equal to this function that we were given, and it's just nicer to deal with. Now notice that we're looking for the limit as x approaches 2. So what I'm going to do is I'm actually going to take this function and create a piecewise function and see what's happening at around that x value of 2. So we're going to be working with this factor more so than the absolute value of x squared. So the absolute value of x minus 2, if we were to just take that and create a piecewise function, what would it be? Well, it would be x minus 2. It would stay x minus 2 as long as x minus 2 is positive. Because if it's positive, then we don't have to take any negatives, convert them to a positive. So it would just stay at x minus 2. But if that expression within the absolute value is negative, then we got to take that expression x minus 2 and multiply it by a negative in front, like that. Now, if you're just looking at this absolute value of x minus 2, then notice that this is going to be defined at an x value of 2 as well. So we can either let this be less than or equal to 0, or this be greater than or equal to 0. However, notice for this function here, it's not going to be defined at that x value 2. We already mentioned there's going to be a hole there. And so here, you can put that, but for this function, you can't put that equal sign. So I'm just going to actually leave this, because we're relating this to this, as that right there. Okay, so taking this and inputting it here, what we're going to have is x minus 2 over absolute value x squared times positive x minus 2 when x minus 2 is greater than 0. Right? When it's positive, then this just stays how it is. But if it's negative, then we're going to have x minus 2 over absolute value x squared. And then I'm going to put a bracket here. This expression has to get multiplied by -1 when that expression is negative. And I put a big bracket here. I mentioned this in the previous example, just because I don't want you to think that it's x squared minus x minus 2. All right, it's the absolute value of x squared times -1 times x minus 2. We're multiplying these three things. Right, this negative you could even put in front here if you want. I'll just keep it there for now. So simplifying this, notice that these x minus 2's cancel out. We're left with a positive 1 up there. And then notice these x minus 2's cancel out, and we're left with a -1 here. And we could bring that -1 up top. And so continuing this up here, this is going to be 1 over the absolute value of x squared. That's going to happen when x is greater than 2. And then this is going to end up being -1 over the absolute value of x squared. And that's going to happen when x is less than 2. And remember, at that x value of 2, the function is going to be, this function is going to be undefined, right? But I'm not going to write that there. And notice that we have to keep this absolute value in this piecewise function because we didn't deal with an x value of 0 within the piecewise function. Right? If we were to deal with this absolute value, then we would have to deal with that x value of 0. But notice that because we're dealing with this limit, I'm just going to keep that absolute value here. And actually, the next point I want to make, if you think about it, 1 over the absolute value of x squared is the exact same as 1 over x squared. We don't have to put an absolute value because anything squared is always going to be positive, except for 0. There's going to be a vertical asymptote there. But any other number, if we have a negative x value, if we square it, it's going to be positive. And if we have a positive x value, if we square it, it's going to stay positive. So we actually don't even have to write that absolute value. This and this are the exact same thing. So we can actually get rid of this absolute value and just put 1 over x squared and then -1 over x squared. We don't have to get rid of the absolute values, but I'm just going to do so anyway. This and this are the exact same thing. Now, 1 over x squared, it's actually very similar. If you remember in the previous example, we had 1 over the absolute value of x. The shape is very similar to that. Basically, all of the, this is 1 over x squared I'm about to graph, all the y values are going to be positive. So it's going to look like that. Okay, and how it actually, it has a similar shape to this, right? Remember with this function, all the y values were positive. That's why that portion got reflected. It has a similar shape, but it's a little different. Like if you were to take both of these functions, kind of going off on a tangent here. This has nothing to do with the question, but I kind of want to show you how 1 over x squared and 1 over absolute value x look like. If you were to take both of them and graph them in Desmos, 1 over x squared would, this would be 1 over x squared. And then let's graph 1 over absolute value x. 1 over absolute value x is going to look like that. And they're going to intersect at 1 and 1 and -1 and 1. right? So the blue graph is 1 over absolute value x, and the graph in black is 1 over x squared. So they are different graphs, but the shape is similar. So thought I would mention that. If you take both of these, graph them on Desmos, you should end up seeing something like that. Anyway, not too important, but 1 over x squared, it looks like this. Well, how is negative 1 over x squared going to look like? Notice that the denominator is always going to be positive, or it's going to be 0, but there's going to be a vertical asymptote there. But for any other x value other than 0, the denominator is always going to be positive. Any x value that's negative, squared, positive. Any x value that's positive, squared, positive. But then we're going to be taking a negative number and dividing it by a positive number. And so it's basically going to be this graph just reflected in the x-axis. So it's going to look like that. So that's how negative 1 over x squared looks like. This is how positive 1 over x squared looks like. And now that we know how both of those look, we can graph this piecewise function. So let's start off with 1 over x squared. Now 1 over x squared, it looks like this. But notice that it's defined for x values greater than 2. So let's say an x value of 2 is right here. If we take an x value of 2 and we plug it into here, it would be 1 over 2 squared, 1 over 4, right? Or 0.25. So the y value here is going to be 1 over 4. And again, this function is defined for x values greater than 2. So all of these x values. So I'm actually going to erase all of this here. And because it's not greater than or equal to 2, it's just greater than 2, this here is going to be a whole. Right, so that's that piece. Negative 1 over x squared, we know it looks like this. And if we plug in this x value of 2 here, we'd end up getting negative 1 over 4. And that's for all the x values less than 2. So basically, we would erase all of this portion. It's not defined for 2 there either, so that's a whole as well. So this graph looks like this. If you were to take this, plug it into Desmos, you should end up getting this graph over here. And now that we have that, we can find the limit as x approaches 2. And hopefully you could tell, if I let this be f of x, what's the limit as x approaches 2 from the negative side of this function? Well, as we approach 2 from the negative side, the y value is approaching negative 1 over 4. As we approach it from the positive side, the y values are approaching positive 1 over 4. And that means that this limit that we were given, like the previous example, does not exist. Because as we approach 2 from both sides, we're approaching different y values from the left and right. And so that overall limit does not exist.